Good morning, all. Welcome to the day two AACT sponsored short-term training program on design of experiments in engineering. In the day two, we have with us Salma Shaik from University of Toledo. She is pursuing her PhD from University of Toledo. And good morning to our principal, Lakshmi Prasad Garu, and convener BVRIT HOD, Mulikrishna Garu. So before we proceed, let me have introduce today's speaker. I know her from my BTech, so we pursued together, and she was very active in after the. I'm sorry, this PPT. Oh, come on, 1 second. Yeah. So we have. BTech together. So after that, she went for pursuing her MS from University of Toledo in the industrial engineering, and later in the same university, she's pursuing her PhD from professor, and she has served as a part-time faculty as a MIM department teaching undergraduate and graduate courses, and lead specialist in the solid waste minimization projects in collaboration with Locust County in Toledo, Ohio. And she has a very over 8 years of experience in both corporate and academic sector. And her research interests include statistical data analysis, machine learning, system analysis and design, quality control and process improvement, sustainability, and criminal justice. And she has proposed many models. During the interaction, I came to know that her proposals were accepted by the community over there, and then they are taking up to the next level. And I requested her on the topic of ANOVA and regression because these models, the application part she's doing it there, and fundamentals are very much needed when we try to propose these models. And that's where she is good at. So I thought I requested, in fact, because of the late hours, it may be troublesome, but still I requested her, and she has agreed. And I think it's 11:30 over there. And thank you for accepting this invitation, ma'am. And I request Lakshmi Prasad Garu to say a few words on the STTP program.
Yeah. Very good morning. And a warm welcome to Salma Madam and all other participants. I really thank Dr. Varun for choosing the resource persons in such a way who are really working in the areas with the relevant topic of design of experiments and related to that the people who are working in field, so that thereby bringing them basically into it. At the moment I could see the research interests of Madam Salma. She sees statistical data analysis, then machine learning, then system analysis and design, quality control and process. See the interdisciplinary nature of the interest that shows basically the present context of doing any of the things in our academics definitely needs an interdisciplinary approach rather than a focused approach on only one thing, because that is what is needed basically for any one of us in the academics. So I'm really very happy to invite Madam to deliver today's lecture basically, and I again thank all the participants also for choosing this staff development program, which is being sponsored by the AACTA. And I'm really very happy about it. Really, the convener of this program, Dr. Mulikrishna, who is the head of the department of the mechanical engineering, who almost I could talk the founder of the mechanical engineering department as far as BVRIT Narsapur is concerned, and who could groom the faculty into that. And his passion and Varun's passion together has culminated into this 1 week program, and I am sure all the participants will take basically the quality inputs of this program and try to implement it. And please remember that probably this 5 day is just to share the fundamentals and the networking. But those who can take these things and then continue that networking and then continue to work in that, definitely we look forward such type of participants. It's not just 5-day interaction. The main intention of the program is not just to conclude in 5 days and that's say goodbye. It's not that. We need to have the continuous interaction even after this program and collaborate and come out with some sustainable products. That is what the meaning of the AICT being sanctioning these type of program. And definitely we at BVRIT look forward to all the participants for such type of interaction in future also. And with this, I again once again thank Madam because for sparing her time at late hours in the night. For us maybe it is like regular thing. For them almost it is 11:30, 11:40 in the night. So but many thanks to Madam for sparing your time, and I am sure with your lecture definitely you enrich the participants a sphere of knowledge in that particular design of experiments. With these words, I thank the participant, the organizers for giving me a chance to speak on this occasion. Thank you all. I wish all the best. Thank you.
Thank you, sir.
Thank you, sir. Sir Mulikishan, sir, you may say.
Good morning to Ms. Salma and good morning to the participants. And thank you for the principal for his words regarding this STTP on design of experiments for engineers. And I have to add 2 points about our principal, sir. Our principal, sir, did his BTech in JNTU Anantapur and MTech and PhD in IIT Bombay. And sir has vast experience about more than 35 years in reputed institutions across the India. And sir joined here as a principal. Before that, sir worked as a principal Geetham University. Thank you, sir. Thank you for your words of encouragement. Thank you so much, sir. And thank you, madam, for agreeing for delivering this session on the session on design of experiments for engineers. Definitely, your expertise will definitely help the participants. Thank you so much for accepting our invitation. Thank you.
No problem, sir.
Thank you, Varun. Please go ahead. Thank you, ma'am. Please go ahead. Thank you.
Okay. Thank you, sir. Okay. I'll remove this sharing so that I can share. 1 second. Okay. Yes, madam. Now you can share.
All right, Varun. Are you able to see here?
Yes. Yes. Okay. But it's not full screen. Now it's okay. At the bottom, one more recording icon is there. Like, fine. Okay. Now it's clear.
All right. Again, thank you for the very kind introduction, Dr. Varun and the principal sir and HOD sir. I just have to be honest that I am a little nervous to be talking in front of such esteemed faculty. You know, I'm still not at that level to present to you guys, but I'm going to try my best to, you know, provide some useful input that might be helpful in your further sessions in DOE here. So as Dr. Varun mentioned, I'm working as a research assistant in the University of Toledo here. My main contributions are in research initiatives. I also serve as a part-time faculty here teaching undergraduate and graduate level courses. And my research areas are like widely diversified because of the machine learning and data analytics concept, almost those and design of experiments. These can be applied in any field of scientific research. So that gives me an opportunity to work with different professors across the university and across the location here. So with that said, I will just jump into the session. So so as you might have already had an introduction to DOE in your first session, but I just outlined a brief overview of the different topics that I'm going to cover here. Now, most of these topics might be already familiar to many of you people there, but just consider this as a revision, maybe revisiting these basic statistical concepts so that these things will be fresh in your mind when you are moving ahead with further complicated DOE concepts, right? So in my presentation today, I'll first begin with explaining key statistical terms, like for example, what is sample and what is population, what is the difference between those two and stuff. And then we'll move on to the concepts of hypothesis testing. We'll discuss t-test and ANOVA. We'll understand what exactly is the ANOVA methodology, how to conduct an ANOVA, when and in what situations to use it. We'll also have a brief discussion about regression. Throughout the presentation, we'll be using Excel and Design Expert to see how to use these tests and all. So just to briefly revisit the definition of an experiment, right? When we have to explain what is actually meant by an experiment, it is nothing but a test or a series of predetermined runs that you conduct in order to understand an existing process or to better understand a new process that you want to implement. Okay. Now, so throughout my presentation, I'm going to use some general examples, everyday examples, which will help us to understand the basic concepts much clearer here, right? Say, for example, you want to conduct an experiment to determine what factors affect the height of a plant, okay? Now, there could be many factors that would affect the growth of a plant, but let's say, for example, you shortlisted only these factors for your analysis. So each of these variable listed here is called a factor, which will have some effect on the height of a plant. Now, some of these factors would be controllable factors. That means you can control those factors, like at what level you want to test those factors. For example, seed variety. You can control what type of seed you want to use for the plant, right? And amount of water, how much water you want to supply. So these are controllable factors because these are in your control. Now, uncontrollable factor, the best example would be, say, probably amount of sunlight or temperature of the day. Okay, that is not in our control. But what we can do is, for these uncontrollable factors, we can try to minimize their effect as much as possible, as much as we can. For example, temperature, right? If you want to conduct this plant height experiment, what you can do the best is you can look at the weather forecast for a month or for a week, and then you can choose, okay, these are the days in which the temperature is moderate. So let me go ahead with these days. That's the maximum you can do over there, right? If the temperature gets extreme, then that is out of your control. But so extending this concept to the topic of design of experiments, again, this diagram just correctly encapsulates what a design of experiment is. So you identify what process you want to study here, and then you identify a set of inputs that you think are important to observe a desired output, which is a result of this process here. Okay, and as we have seen, some of the factors are controllable and some of the factors are uncontrollable. Now, just to give a brief overview of DOE here, as you can see from this graph, the applications of DOE have skyrocketed in the field of scientific research, especially starting from 1970, there has been an exponential growth in the applications of DOE, and it is just predicted to increase further. If you want to see in what scientific areas the DOE is applied most, as you can see from this graph here, the top application is in the field of medicine. This is mostly in when pharmaceutical companies, they want to introduce a new drug, when they want to conduct patient trials, DOE is like widely used over there. But you can also observe that engineering is not far behind. It's the second most fastest growing area. Again, as you can see from this chart here, DOE is just not limited to engineering, right? You can see very different fields, like for example, nursing or veterinary, even dentistry. So DOE is like, it's almost like a life skill here, which you can apply no matter what field you pursue and what your research goals are. Now, having said that, we'll move on to basic statistical concepts here. So the first important distinction that we have to understand is between sample and population. Okay, so what is meant by sample and what is population? Again, I want to take a very basic example here. Suppose you want to find out the average height of all the students at your college or at your university. Okay, just a general example. So what is the approach? What is one approach that you can do? You can go ahead and measure the height of every student on your campus, right? Let's just say you have around 5,000 students in your campus. Is this doable? Yes, it is doable. But is it effective? I wouldn't say it is effective, right? Because it will take so much time. There is no need for us to go ahead and measure the height of each and every student. So this 5,000 student, that data or that number is known as the population, nothing but all the possible values for your subject of interest. Okay, that is the population. So, but most of the statistics, we never work with population directly, okay, because of resource constraint, because of inefficiency, because of n number of reasons. So what we do is we always take a subset of this population. That is, you just choose a small set of this population. So instead of measuring the height of 5,000 students, you'll just randomly select 50 students on your campus, right? So now these 50 students, it will become your sample. So the statistics in a nutshell is working with a sample of data, and using the data that you obtain for that sample, you try to estimate what could be the characteristics of the population, right? So say for this sample of 50 students, if we get the average height as 5 feet 7 inches, we'll say that based on our sample data, we estimate that. We never say definitive statements in statistics, like this is what it is. We always say we estimate or we infer that the population mean or the average height of all the students or any student on the campus can be 5 feet 7 inches. All right. So this is the basic idea. Now, some of the basic statistical characteristics are mean, standard deviation, and variance, which we all know here, right? Mean is nothing but average of all the data points. Standard deviation and variance, they just show you the amount of variation in your data set, okay? So when we calculate these characteristics for a sample, those are known as sample statistics, all right? And calculating these values for a population, then those would be known as population parameters, all right? So we can say we use sample statistics to estimate population parameters. And some important notation that we have to understand here is, if you see in this table, these characteristics calculated for a population or population parameters, and these are the important notations that we have to remember. Mu and sigma are for population mean and standard deviation, and X bar or Y bar and S are for sample statistics. You'll see in most of the formulas, in most of the statistical analysis, you'll always see these variables in your formulas here, because we're always working with a sample. Again, just simple formulas here. Mean is nothing but the average of all the data points here, and variance is nothing but it just shows how much each data point. So yi is nothing but one single data point for you. So it's just what is its difference from the overall mean, and summation of all those difference would be your variance. And when we talk about standard deviation is nothing but square root of this variance. Okay, so this will be your standard deviation. So mu gives what is the average value. Standard deviation says how wide is this spread, by how much are the values varying. Are they very close together enough, or is there a large difference in the values? Another important concept is called sampling distribution here. Okay, so as we said, from a population, we always take a sample. Now you can take 50 sample students. The next sample, you can choose some 50 different students. Okay, in that way, you can take n number of samples. And for each sample, when you calculate, say, mean for the data set, that is known as a sampling statistic. Okay, and the distribution of these sample statistics is what is known as a sampling distribution. A distribution is nothing but it shows all the possible values that a variable can take. Okay, what is the structure of its distribution? So this diagram just highlights whatever concept we have been talking. We'll have an overall population. From that, with the method of sampling, there are many different types of samplings: random samplings, convenient samplings, okay, different types of samplings. You'll choose the type of sampling method that you think is appropriate for your experiment, for your analysis. And based on that sample, you will make inferences about your population. Okay, and that is again known as inferential statistics. Now, as you know, this is the normal distribution curve, which is like probably the most important probability distribution curve. Almost a lot of natural phenomena can be fit into the normal distribution. All this says is, it says in most of the processes, most of the values are like, there are very few extreme values. Say, for example, I'll take with an example which will be more clear. If you want to assess the performance of students in a class, right? You might observe that most of the students fall in the average range. Almost 70–80% of the students fall in the average range. There are very few students who are like really low performers in the class, and there are very few students who are like exceptionally high performance. So again, this is a normal distribution curve here. Another example is if we look at the height of US women, right? It has been observed that it ranges from anywhere between 5 foot to 5 foot 10 inches here. Again, almost 80% to 90% of the people are within the range of 5 foot to 3 inches. Okay, so in this way, any phenomena, any process that occurs can be represented in the form of a normal distribution curve here. The next important topic is what is known as a standard normal distribution. So as we have seen in the previous slide, there are many phenomena that we can fit onto a normal distribution, right? But what we do is we standardize every normal distribution to something known as a standard normal distribution curve so that we can use standard statistical tables and statistical analysis. So the way we do that is, say for example, we have 3 data points, okay, x1, x2, x3, just some random numbers, say 5, 4, or 7 something. These are your data points for some measurement, right? So what we do is we convert each data point into something called a z-score, okay? And this is the formula for the z-score. All it does is it takes your individual data point, it subtracts the mean of the entire data set from it, and then it divides with the standard deviation. Now, of course, as I said, since we always work with sample data, this mu and sigma would be replaced with x bar and s as needed, okay? Now, when we convert all these observed data points into z-scores, and when we chart those z-scores, this will be the normal distribution curve again. And its characteristics are that its mean would be 0 and the standard deviation would be 1, okay? And I think the next chart would be more familiar to you might be. So as you can see here, on a standard normal distribution curve, almost 68% of the data points fall within 1 standard deviation of the mean, okay? And almost 95% of the data, it will fall within 2 standard deviations of the mean. That is, any point that you take, 95% of the points will be within that range, 2 standard deviations of your mean. And the most important methodology in manufacturing, if you can take, it is called as Six Sigma methodology, right? Many manufacturers, they aim to obtain Six Sigma quality control process in their operations. That is nothing but they want to make sure that almost 99.7% of their products are defect free. That is, they are meeting the specifications, the Six Sigma specifications that they have set up. Okay, now what I want to do is we'll just take an example and we'll conduct some statistical analysis to say how to apply these concepts. Okay, so I have extensively used this textbook, Design and Analysis of Experiments by Douglas C. Montgomery. It's really one of the best resources for DOE out there. So I have taken this example from there. So in this example, an engineer, he is testing a new method of cement formulation. Okay, so there is an existing method of cement formulation, cement or mortar, and he came up with a new method, okay, new method of mixture. Now he wants to check whether this new method has a different effect on the tension bond strength of the cement. Okay, he just wants to compare these two and wants to understand, is the new method any better or is it any worse or is it not different than the existing method? All right, so that is his aim. So he already has an aim in his mind. So once you have your aim in your mind, once you know what you want to study, then you'll go ahead and you'll collect the data for that. Right? So in this case, he has 10 observations for the existing method and he has 10 observations for the new method here. So overall, we have 20 observations. All right. So this is the basic premise of the experiment. So any statistical inference method, no matter what field you are doing your analysis, there are some basic steps, some standard steps that we follow. Okay. So first step is always you have to visualize your data. Right? So you just have to get a visual image of your data set. You want to see, okay, how is it varying? Is it all concentrated at one point or is it gradually increasing the data or is it, randomly scattered around? So you can use some visualization tools such as dot plots, box plots or histograms, and there are many number of tools. So depending on what works best for you, depending on your prior knowledge or your expertise, you can choose those kind of visualization tools. And the second step is always to get the descriptive statistics. Nothing but basic mean, variance, and standard deviation. It will just give some perception about the data. Okay, like what am I looking at here? Okay, it will just give that information. Now this information, it will not be helpful to make any useful inferences about the population, about the processes that we are studying. All right. So for that, we have to do more rigorous statistical analysis. And that's where the concept of hypothesis testing comes into picture. Okay. All right, so first we'll try to see for our example, if the graphical view or the visual analysis gives any information, right? So what I have done here is I have just plotted a scatter plot for the 2 types of formulations here. Now, as you can see, the orange dots represent the unmodified mortar or the old existing method, and the blue dot represent the new method. The first look at this data, I cannot say what's going on here. I don't know which one is gradually increasing or which one is gradually decreasing. It just looks randomly scattered. Maybe if we draw the trend line, does it show any better? I don't know. I still cannot say for sure, right? Maybe the first look, it gives that the orange line is kind of at a slightly higher tension bond strength. So the orange one represents the existing method. So is the existing method better than the new method? Maybe, but I'm not sure because this is only one sample. What if we take some other set of readings? It might give a different graph over here, right? Same way, if you look at the box plot here, okay, box plot is another visualization tool here. So here, the blue one, it represents the new method and the orange one is for the existing method here, right? So this is also known as a box and whisker plot because these two horizontal lines at the end are known as whiskers. They represent the minimum value and maximum value in your data set, okay? And there is a small cross mark in here. I'm not sure if you're able to see. So in each box here, there is a small cross mark that denotes the mean of the entire data set. And there is a horizontal line here that represents the median of the data set. Okay, so this again, it gives you an overall picture of the data, right? Okay, so where is the mean? Where is the median? How are these two data sets comparing against each other? All right, again, looking at this, you might think that the unmodified mortar still has a higher tension bond strength, okay? But again, can we make conclusions on this? Not really, because again, this is only for one particular sample. So the next step, as we discussed, is to look at the sample statistics. Okay, so we can see here we have calculated mean for two types of cement formulations and the variance and standard deviation. This again doesn't give much information because they're not really that different. So we'll move on to hypothesis test framework here. So this is just some of the basic steps that I have outlined that we need to take in order to conduct a hypothesis test. Okay, so the first step so what is a hypothesis? Hypothesis is nothing but a claim. Okay, in simple words, it is a claim. It can be a claim about an existing process. Okay, or it can be claim about a new process. All right. Existing process. You want to say that, okay, my process is so efficient that it always produces steel rods of 1 meter length. Okay, it always produces steel rods of 1 meter length. My process is so efficient. So that is your existing claim. But somebody comes and says that, okay, I'm not sure your steel rods are always 1 meter. I'm not sure about it. So then you conduct a hypothesis test to check whether your existing claim is valid or not. Okay, a new process is, say, for example, in health science, in medical field, when you are releasing a new drug into the market. Okay, you are making a claim, my new drug is very effective. It's 50% more effective than the existing drug in the market. So that is, you're making a claim about a new process or a new product. So these are the two situations in which you can use the hypothesis testing setup. Okay, so depending on what you are trying to test, you will set the hypothesis. So if we take our cement formulation example, the engineer he wants to test the new method against the old method. Now he doesn't know whether his new method is better than the old method or it is worse than the old method. He doesn't know which way it is. So what he says is his null hypothesis. So these are the notations here. Your null hypothesis, which is nothing but the existing situation, existing condition. It is the null hypothesis. So for the null hypothesis, the claim is that mean of the existing process, that is mean of the tension bond strength of the cement obtained from the existing process, is no different than or is equal to the mean of the tension bond strength of the cement obtained from the new process. That is the existing claim. That it is not any better or not any worse. It is just what it is. So the alternative hypothesis, the engineer comes and says, no, I'm sure there is some difference, but I don't know whether it is good or bad. I know some difference. So he comes and he sets up an alternative hypothesis, which will be two-sided. It will be like this. He'll just say it is different. That's all. I still don't know whether it is good or bad. Right? So this is known as a two-sided hypothesis because it can go either way. Okay. And one-sided hypothesis would be when the engineer is very sure that his new method is better than the existing method. He's like 100% sure. So in that case, your null hypothesis would be like this. That is, your new method is better than the old method. If he is very sure it's the other way, that the new method is bad than the old method, so your hypothesis formulation will be like this. All right. So the first one is known as the right-sided hypothesis, and this is the left-sided hypothesis, or just one-sided hypothesis. All right. So one basic rule that people follow is you should always try to go with a two-sided hypothesis unless you have a very strong reason to go with one-sided hypothesis. Because the disadvantage is if you make a one-sided hypothesis set up by mistake, then you are missing what happens on the other side. You cannot know what happens on the other side, right? So this should be taken only in cases when you are absolutely sure about it. So once you set up your hypothesis like this, then you go ahead and collect the data for your experiment, okay? And after you collect the data, you set up something called as a significance level. This is a very critical concept here, okay? So it's nothing but, so whenever you want to make some conclusions out of your hypothesis, we can never be 100% sure about our decisions, right? Especially in statistics, you can never say that I'm 100% confident. You will always say that, okay, I'm 90% confident or 95% confident, like that. So you have to determine how much percentage confidence you want to have in your process, okay? How much confidence you want to give about your process. So that is something that you set up on your own, depending on your priorities, depending on your process, okay? So if you say that I want to be 95% confidence about my analysis, okay, about my conclusions, so this 95% will be known as your confidence level. All right. Now, alpha is nothing but, it's also denoted with this Greek letter alpha here. Alpha is just 1 minus confidence level, okay? So now if your confidence level is 95%, your alpha would be 1 minus of 95%, which would be 5% or just 0.05, all right? So usually 95% confidence level, which leads to an alpha of 0.05, is most commonly used in experiments, most commonly used in research areas, okay? Definitely, of course, there are people who use 90%, and there are situations where 99% confidence levels are also used. But it depends again on your experimental setup, on your research aims and all that stuff. But this is the most commonly used alpha level here, all right? So you set this up, you set up the significance level. The other way of saying the significance level is for how much percentage of the time are you willing to be wrong about your analysis. That's the other way, right? So if you're 95% confidence about one process, what does that mean? You're not confident about 5% of the time. That means you agree that you may make mistakes 5% of the time. So that's the concept here. Now, once you set up your hypothesis, once you set up your significance level, then you have to go ahead and decide upon what kind of statistical test you want to conduct, okay? So there are many different types of statistical tests like z-test, t-test, chi-square test and all, and there are different criteria and different situations wherein you might choose what test to apply. So we have to make a selection depending on our data set and the significance level and those kind of things, okay? Once you have, so left side is all your setup process, okay? Left side, 4 things are all your setup process. Now, once you have all this ready, then you go ahead and do your calculations. So the 2 main things that we calculate in statistical analysis are something called test statistic. This you will calculate based on your sample data that you have in your hand, all right? And there will be a formula for the test statistic depending on what test you are using, that we'll see, okay? And the next quantity that you calculate is called as the critical value. Now, this critical value is obtained based on your significance level and based on your sample size, like how many observations you have. And from where do we obtain this? We obtain it from something called a distribution table. So no matter what statistical test you choose, each statistical test comes with a standard distribution table, which has some values corresponding to your alpha level and your sample size, okay? So once you have these 2 values, test is simple. You just compare these 2 values, and depending on whether the value is greater than or smaller, you make a decision. We'll see this with an example, then it will be more clear on how to compare these values and how to draw inference. Okay? So at the end of your statistical hypothesis, you can come up with only 2 conclusions. You can either reject the null hypothesis. Okay, so what was the claim here? The null hypothesis said there is no difference in the formulation. So you can either reject that claim, you can say that no, that is not right. I have enough evidence to say that this null hypothesis is wrong. And that will be again dependent on your values that we calculate here. Okay. So you can either reject the null hypothesis or you can fail to reject the null hypothesis. So it's very rare to accept the null hypothesis, accept the alternate hypothesis. So mostly like a preferred way of putting out your conclusions is either saying that I have enough evidence to reject the null hypothesis or I don't have enough evidence to reject the null hypothesis. That means you're indirectly accepting the null hypothesis. All right. So just to look at the types of hypotheses on a graphical view, say in a two-sided hypothesis, once you have your test statistic calculated from sample data, and once you get your T critical value from your distribution table, you go ahead and try to draw this region here. Okay, so we assume a normal distribution, and say for our example, the null hypothesis was, alternate hypothesis was two-sided, right? So when you have a two-sided hypothesis, your alpha would be split into half because you want to account for both sides. Okay, so if you have alpha, you're on the right side, you'll have alpha by 2 region, left side, you'll have alpha by 2, right? So that means if our alpha is 0.5, and we assume that the area under the curve, because this is just a probability distribution, right? So the possible values of probability are anywhere from 0 to 1, that's it. So we'll assume the area under the curve is 1, and that is 100%. So in this, if you are 95% confident, that means you are 2.5% and 2.5% not confident on either side. That is just your alpha. So if your alpha is 0.05, in this case, here your alpha by 2, this will become 0.025, and this will be 0.025. Okay, so this area is 0.025, and this area is. So all we do is we compare our calculated test statistic against the critical value. So this T alpha by 2 here, nothing but the value that you obtained from the table. So if our value, if our T naught, nothing but the test statistic, if this falls beyond the critical value from the table, beyond the critical value, then we reject null hypothesis. Okay, then we say that this did not happen by chance. That is, there is definitely a difference in the means. That's why we observed a value this extreme. So that is the ideology behind it. All right. If you take one-sided hypothesis here, so on the one-sided hypothesis, I'm sorry, so this is left-sided hypothesis. I think I told you the other way. I'm sorry about that. So the left-sided hypothesis, it's only one-sided, right? So all your alpha would be only on one side here. So this area will be 0.05 for you. Same way for right-tailed hypothesis, it will be 0.05. Again, the same concept. You'll calculate the test statistic. You'll compare it with the critical value from the table. And if it falls beyond this, then you will say that, okay, this is falling in my rejection region. It is very extreme. That it did not happen by chance. Okay, sometimes things can happen by chance, right? Maybe just this sample showed a difference. Maybe it's not actually, but when you get a value this extreme, we say that this could not have happened by chance. Now, next important concept is called type 1 and type 2 errors. These are important to understand because depending on how we understand this, which one is important, we actually set up our alpha levels in the experiments. Okay, so type 1 error is nothing but it is when you reject the null hypothesis when it is actually true. Okay, when it is actually true, but you falsely reject the null hypothesis. That is, then you are committing a type 1 error. Type 2 error is when you fail to reject the null hypothesis. That null hypothesis is false, but you fail to identify it. You wrongly accept it. So that is a type 2 error for you. Okay, I just want to take a quick example here, and then, or I think I have a different table. All right. So if you just put it in a matrix like this, right, you have a null hypothesis, and you can make only 2 decisions about your null hypothesis. That is, you can either accept your null hypothesis, that is fail to reject, which is indirectly accepting, or you reject your null hypothesis. Okay. Now, say in reality your null hypothesis is true and you correctly accept it, then you have made a correct decision, right? In reality your null hypothesis is true, but you falsely rejected it thinking that it is wrong, then you have committed a type 1 error. The opposite is type 2 error, which is in reality your null hypothesis is false, but you accepted it by mistake or by wrong statistical analysis or by wrong interpretation. So that is, you have conducted a type 2 error then, which is also known as beta. The last situation is wherein your null hypothesis is false and you correctly identified it and you rejected it. Then you have made a correct decision. Okay, so there are always 4 possibilities, 2 correct possibilities of making 2 right decisions and 2 wrong decision possibilities. Now, I just want to explain this with another example here because this I used to get confused about this, and so there is a famous example that people use to explain about type 1 and type 2 errors, right? Which is the example of guilty or not guilty. Say a person is convicted of a crime or accused of a crime. So one basic rule in court of law is that everybody is innocent until proven guilty, right? Innocent until proven otherwise. So that's why we have lawyers and court system and all that, right? Everybody who is accused of a crime, they go to a court and they try to provide evidence either against them, and the opposition provides evidence against them, you know. So until somebody is proven guilty, they are considered innocent. Now let's try to apply hypothesis testing to this, okay? And so a null hypothesis, say a reality is that that person is actually guilty. We don't know whether he is guilty or not. Let's assume that this is the reality, that he is actually guilty. Now, what are the two decisions that we can make here, or that the judge can make, depending on the evidence? He can either accept that he is guilty, or he can reject that the person is guilty, okay? Now, what happens if a person is guilty and we correctly accept that that person is guilty? Then we have made a right decision here, right? Now, if a person is actually guilty and the judge fails to know, you know, infer that, then judge has made a wrong decision. So that means we are letting go of a criminal who committed a crime, but we are not giving him any punishment because we made a wrong judgment here. Now, let's take the other scenario, that the person is actually not guilty. Actually not guilty, right? Now, in this situation, in reality, the person is not guilty, and you accept that the person is not guilty, okay? So, all right, so here also we have made a right decision, right? Because he is not guilty and we are accepting that he's not guilty. But what if he is actually not guilty and you are rejecting that? That means you are saying that he is guilty. You're accusing a person of a crime when he did not do anything. So again, you made a wrong decision here, okay? So which one do, again, so this is type 1 error, this is type 2 error, right? So which one do we think is more worse here, right? We think accusing a person of a crime when he did not commit is more worse, right? So why this is important is alpha and beta are related. When you set up your significance level, you are indirectly affecting your type 2 error also. So as they are inversely related actually. So as your alpha increases, your type 2 error decreases. As your alpha decreases, type 2 error increases. So you have to make a decision depending on what kind of error are you willing to make. So in this case, we do not want to put a person, innocent person behind bars, right? So we want to reduce our type 2 error as much as possible. That means you can have a wide range of alpha. But then again, we cannot just keep on increasing. There should be a balance. But I hope you got the big picture. That so how you determine how to set up your alpha, it depends on the severity of the wrong decision. That is, if you make a wrong decision, how worse it is. So depending on that, you choose your alpha significance level, okay? So keeping that in mind, we'll look at the t-test here. So as I said, as part of the hypothesis test, once you set up your significance level, the next step is to choose the correct statistical test, right? So in our case, we had two samples, modified mortar and unmodified, modified and unmodified. And we don't know the population variances. It's nothing but we don't know the variance of the entire, if we just go ahead with the new formulation method, we don't know what variance could be. So we don't know the population variance. In such cases, we use t-test. If the population variance was known, then we'll go with the z-test, okay? Either the population variance is known, or in some cases, people say that if the sample size is greater than 30, even then you can just go ahead with the z-test, right? But in our case, both these conditions are failing. We don't know the population variance and we don't have a sample size greater than 30. So we'll stick with the t-test statistic here. And this is the formula to calculate the t-test statistic. Here again, y1 bar and y2 bar are nothing but the averages of the two data sets. S1, S2 are the, S1 square, S2 square sample variances and then sample sizes. So as we already saw, first quantity that you calculate is t-test statistic. The second quantity that you calculate is called t-critical value, right? So as we discussed, in order to get the t-critical value from a t-distribution table. So this is a t-distribution table. We'll see how to get a value from this in the next slides. So in order to look at the value, we need something called degrees of freedom and significance level. Significance level is again our alpha here, and degrees of freedom depends on your sample size, -2, because we have two groups, so -2. One more assumption that the example provider made here is that he's assuming that the population variance of the two formulation methods is same. Okay, so this affects the t-test statistic formula here, and instead of S1 square by N1, he just took the variance outside of the square root. Now this will be known as the pooled pooled standard deviation, okay? And this would be the formula to calculate that. Again, it just depends on S1 square, variances and sample sizes. Now, substituting all these values, we get all these values from our data set, right? We know the sample size, which is 10 for each type of mortar formulation, and we can calculate the variances from the data points. And substituting all these values, we obtain our t-test statistic to be minus 2.20. Okay, let's remember this. Our calculated value was minus 2.20. Now, the main question that we are trying to answer is, okay, how extreme is this? You know, is this enough for me to say that the variation in the mean is not by chance? That is, there is some inherent difference in the processes. So in order to make the decision about how extreme it is, we rely on the t-critical value, okay? So for this case, our degrees of freedom would be 18 here and significance level is 0.05. Now let's look at the table here on how to see. So if you look at this, so these standard tables, they can be found anywhere, you know, at the back in the appendix section in a statistics textbook or a DOE, or even online. Some universities provide this. And okay, so we have to remember that our alternative hypothesis was two-tailed, right? Okay, it was two-tailed, and so this would be the row for the two-tailed hypothesis, and so this shows the significance. So what was our alpha here? Significance, it was 0.05, right? So this would be the column from which we'll get our critical value. Okay. Now along the horizontal rows here, we have degrees of freedom. So how many degrees of freedom do we have? 18. So we'll just draw a line from 18 here, and we can see this value. 2.101 is our critical value. All right. So again, we have to remember this is a two-tailed test. So this 2.101 will be on either sides of the distribution. So plus 2.101 would be on the right tail and minus 2.1 would be on the left tail here. All right. So how to make inference now? Okay, let's just write down here. So our test statistic was 2.20, and the critical value that we obtained from the table was minus 2.1 on either side. So I'll just say plus or minus 2.1. So what we do is here, we'll just draw our own normal distribution curve for the example that we are doing here, right? So again, standard normal distribution curve, mean would be centered at 0 here. And let's try to show these values on this graph here. Let's first start with our critical value, which we obtained from the standard table. Okay, so two standard deviations. So 2.1 is almost two standard deviations away from the mean, right? So one standard deviation, two standard deviation somewhere over here. So this would be our T critical value of 2.1. Same way on the other side, on the negative side, lower side, 2.1 somewhere around over here. This will be minus 2.1. This is our critical values. Now let's show our calculated values. Okay, so our calculated value was 2.20. Again, this will be plus or minus 2.20 because it's a two-tailed test. So plus 2.20 on the right hand side, it will fall beyond 2.1. Okay, so this will be 2.2. Similarly, on the left hand side, negative 2.2 is again less than negative 2.1, right? Negative numbers like this. So this will be minus 2.2. So now your acceptance and rejection region are nothing but, so this is your acceptance region, okay? Anything that will fall between the values that we obtained from the table, that shows a normal process. That means that shows means are similar. But our calculated value here, it has fallen in the rejection region beyond the values, okay? So we say that there is this value is so extreme that it might not have happened by chance. That means the means are not equal. Sorry, existing process and new process. This was our null hypothesis. So we say that since our calculated value is falling in the rejection region, we conclude that this did not happen by chance, and we have enough evidence to say that the two formulation methods are not similar. All right, so this is how you make inference based on critical value and test statistic. Another very common method that you will see in design of analysis examples and experiments that you see in the future is called the p-value approach. Okay, so the p-value approach, what it does is it makes use of significance level. So our significance level was 0.05. Let's keep that in mind. And what it's also called as a p-value because it's just the probability value under the curve, right? So this is our standard that we have set. Now we have to obtain the p-value or the alpha value corresponding to the test statistic that we obtained. Okay, so the value that we obtained was 2.20. Now let's go back to the table here. If you pay attention, our value was 2.20, right? But okay, let's see. I'm sorry, I tried to make this bigger, but I'm just using two devices and it's okay. So we have, so 2.101 was the value corresponding to alpha 0.05, okay, that we can see here. So 2.101 was the value corresponding to alpha 0.05. Now, what was the value that we obtained? 2.20. It must be somewhere beyond 2.101, somewhere here, right? Now, all we are trying to do is we are trying to get the area under the curve or the alpha value corresponding to the test statistic that we calculated. But as you can see here, the next value available is 2.552. So we can assume that our value, the p-value corresponding to 2.20, it will be beyond, right? Like less than 0.05. It will be between 0.05 and 0.02. That we can say. We don't know exactly what value, but I can say that it's between 0.05 and 0.02. Okay. Now again, this is a two-tailed test. If we want to check on either sides, what might be the area? So we'll say that on each side, the area corresponding to the value that we calculated will be 0.025 and 0.01. Okay. So this is, no matter what value we get between this, our significance level for two-tailed was 0.025, right? So now you just compare this range with the significance level that we set. So it's always going to be less than what we set here. Okay, so again, on a normal distribution curve, it's going to fall beyond 0.25 region area. Maybe that will be only this area here, corresponding to the p-value for our test statistic. So again, based on p-value also, we can say that it is very extreme. It is so small or it is so extreme that it didn't happen by chance. So these are two methods of inference. Now we'll just quickly go to Excel here and see show how I conducted this in Excel. So this is the sample data that we had for our example, right? Modified and unmodified. So I'm going to disable something and okay. So in order to conduct we can conduct a lot of statistical tests through Excel. In order to conduct any statistical analysis test, we need to have a data analysis tool pack in Excel. So I have a MacBook here. The navigation and options might be slightly different, but they should be mostly similar. You should be able to follow. So I already have an option called analysis tools here. So if I click on analysis tools, I see analysis tool pack and I can add it from.
It's not displayed. It's showing still demonstration in
really?
Excel.
Okay.
Sharing.
Can you see now?
Change. Yeah, now okay.
Okay, I'm so sorry. So, all right. So all I was saying was we have to have an analysis tool pack here. So I already had an analysis tools option here. So I can click on that and I can choose analysis tool pack. Or if you don't have that, we can go to tools, say Excel add-ins here, and you have analysis tool pack, right? And click OK. Then you will get this option here called data analysis. Now, in order to conduct a t-test, all you have to do is you'll go to data analysis. And there are many different options here, as you can see. And you'll choose t-test. We have two sample and we have assumed equal variances, right? So this is the option. You'll say OK here. Now you have to give the input here. What is the range of first variable? So just click on that cell and go ahead and select all these data points. Click the second variable data points here. And then it's asking whether you have labels in your data. It's nothing but whether you have column names, right? So if we check labels, it will identify those as names of the data set over there. And by default, you can see it has set the significance level to be 0.0. You can change that if you want, but that's the basic default we use. And here is just asking where it should display the results. You can either put it in a new workbook or a new worksheet. I usually try to put it in the same sheet so that we can check the data and the results at the same place. So you'll just click on this and you choose a cell anywhere, click OK, and then say OK. So it will just give you the values. Okay. So all we did, the hand calculations, we don't have to do that. Most of the time we use softwares like this, but it's really important that we do some examples with hand so that we understand the underlying concepts. So as you can see here, it calculated the mean for 2 samples, it calculated the variance, and the important things that we have to notice here is t-test statistic, right? So it says -2 point something, but for us, I think we got 2.2, right? But it's okay. It might be because of slight rounding. We might have considered some decimals in our rounding thing, but it's almost close. And the other thing is, okay, T critical, right? So 2.101. This is what we get from the T distribution table. Again, if you compare these two, our value is really extreme. It's showing only on one side, but then, you know, it could be 2 side, or it is trying to say that it's less, you know, it's falling on the left-hand side. That means new method is not better than the old method. The other approach that we saw was with p-value, right? So p-value here, again, the value 0.04, right? From our analysis, we found that it should be between 0.05 and 0.2 something. So we were almost close to that. So no matter whether you take the t-test statistic approach or p-value approach, we are rejecting the null hypothesis. Now we will go back to my presentation. Okay, now moving on to the next example here. In the first example, we had only 2 different formulations, right? Now, what if we have 4 different types of formulations instead of 2? Now, what if we want to study which one of them is better, or which one of them are similar and which ones are different, and how they affect the tensile bond strength? So in this example, we have 4 different formulations, and for each formulation, we have 4 samples here. Okay, 4 different readings of cement formulation for tensile bond strength for 4 different groups. So overall, we have 16 observations here, okay, or 16 runs or observations. The question here is, we want to test the hypothesis that the type of cement formulation, does it have any effect or not? So we'll see how to set up the null hypothesis for this in the future slides. Now, if we want to apply t-test to this, right? If we want to apply t-test to this, what will we do here? T-test can only compare 2 groups at a time, but we have 4 groups, right? So if we want to apply t-test here, there will be a lot of combinations because we can take only 2 at a time. One simple way to calculate how many combinations of 2 you have is just to use this combinations formula here, right? So we have 4 groups. At a time, we want to take 2 groups for our t-test. So this will result in, right? So this will be like 6 combinations overall. That means you have to conduct 6 t-tests in order to get idea about the means of the 4 groups. This, as you can imagine, this is very inefficient, right? Because it will take a lot of time, resources, and it's just like a brute force approach. The other biggest problem with using t-test for comparing more than 2 means is what is called as a type 1 error inflation. This is nothing but, say for example, you have set 95% confidence level for your t-test, right? So this 95% confidence level will be for 1 t-test. So if you conduct 2 t-tests, your confidence level would be 95% times 95%. So I already calculated these numbers, so I'm not that fast at calculations. So I know this is 0.9025. That is nothing but around 90%. So as you can see, with just 2 tests, your confidence level has dropped from 95 to 90%. That means your alpha is around almost 0.1, or you are making errors 10% of the time, whereas we wanted to make only 5% of the time. So I have a really nice table here. I got it from university website. You can go to this link to understand more about the type 1 error inflation, but this is what it is in a nutshell, right? So it just says that if you have 3 groups, your total combinations pairs will be 3. If you have A, B, C, right? Just A, B, A, C, and B, C. You have 3 groups. You have to conduct 3 t-tests. Now for 3 t-tests, your confidence level would be multiplying your 95%, because you want to have 95% confidence in each. So you have to multiply. All 3 have to happen at the same time, right? Or together. So this comes out to around 85%, 85.7%. See what it does to your alpha, right? Your alpha is 1 minus of this confidence level, which would be around 14%. That is what is shown in your table. So with just 3 groups conducting 3 t-tests, our error rate is increasing from 5% to 14% here. So you can see almost how quickly t-test is a bad idea for more than 2 group comparison. We will just move on to the, okay, so these were nothing but I just did some visual analysis for the 4 groups here. I wanted to see if the graphs give any information about the difference in means, right? So maybe the first look says that the second cement formulation technique might be better than all the other 3 because it starts from a higher tensile strength and on an average it's higher than the other. But again, this is just for one set of samples. Similarly, even box plot shows that the second formulation technique is doing better than the other techniques. Okay, we'll just keep this in mind. We'll move ahead with the next analysis. So this is where the concept of ANOVA comes into picture. Okay, ANOVA just stands for analysis of variance. Okay, analysis of variance. What it does is it just goes one step beyond t-test. Okay, so t-test compares means, right? Analysis compares the difference or the variations between the means here. Okay, it's just going a one level deeper. So it's used for more than 2 groups. You can actually use it only for 2 groups, but it's just overkill. It's not needed. T-test is more than enough for 2 groups. So it's more robust to compare. And again, we will not have the type 1 error inflation because it does not do pairwise means comparison. It just considers whole data as one. It calculates variances. We'll see how it does in the next slides. But there is no risk of type 1 error inflation with ANOVA. Okay. And the test statistic corresponding to ANOVA is called F-test statistic. We'll again see there is a formula for this. And okay, as I said, focus is on the variation here, right? So the steps in the ANOVA, this is really tedious, you know, but we'll do an example manually here because we have to understand how the calculations are done. So the first step are we have to calculate mean for each of the groups, right? So we had 4 groups. Or 4 different cement formulations, right? So for each group had 4 data points in it, 4 data points. So first step, what we do is we calculate mean for each of the group, okay, taking its own data points. And the second step, we'll calculate overall mean or mean of all the groups, okay. The third step would be we'll calculate something called within group variation. That is nothing but in a given group, we have 4 data points, right? We'll see how much is the variance for each data point within its own group. That is one calculation. The next calculation is between group variation. We'll see how much does each group vary from one another. So there are just 2 types of variances. One is within group and the other one is between groups here. That is the whole concept of ANOVA. And the F statistic is nothing but ratio of these 2 variations. It's nothing but it will see between group variation divided by within group. That is your calculated F-test statistic. The same thing that I was saying there. So between group variation and within group variation. So again, as with any statistical test, hypothesis test, you will have one test statistic that you calculate from your sample data. And you will have one critical value that you will get from the corresponding distribution table. So F distribution has a separate table depending on what alpha you choose. It has a table for alpha 0, 1%, 10%, and 5%. So depending on what alpha you are choosing, you will pick that corresponding distribution table, okay? And again, we use the sample size and the number of groups to obtain the critical value. So here, we are just trying to see, so ANOVA just sees whether the means are different or not, okay? So the null hypothesis for ANOVA is all the means are different, all the means are same. That is, there is no effect of cement formulation technique on the tensile bond strength. Your null hypothesis would be at least one pair of mean is different. At least one pair of means are different. It can be 1, 2, 1, 3, doesn't matter. It doesn't care, okay? At least one pair is different. So it just takes one-sided hypothesis here because it just wants to see whether it falls in the rejection region or not. So again, we construct a rejection region depending on our calculated test statistic or p-value. And then if our value falls in that rejection region, then we will reject this claim made by the null hypothesis. And we will conclude that no, not all the formulations are not same. There is some difference in them, okay? That is the first step of ANOVA. The same thing that we were discussing right now. So let's go ahead and quickly see how I have. So I did all these calculations in Excel. We don't have to do this manually because this is just, using simple mean and variance formula. So the first step was I calculated average of all these values here. So these would be the values. So this first row is for the first group. This is the average for the first group values. Same way, these are all the averages for the remaining groups. And the overall or grand mean would be just average of all this. You can do it like this, or we can say overall mean is just average of all these data points. Both are same. Both will result in the same number here. Okay. The second step is we have to calculate between group variation. All right. So the same concept of variation we'll use here. So we have 4 different types of mixing techniques, and so the group size of each mixing technique is 4 here. And the group mean for each was here. This we calculated in the previous step. And the overall mean was this. Okay. So the first step in calculating variance is get the difference of individual observation from the overall observation. So this is that column. And in the next column, we just square this difference. And in the next column, we are multiplying by the group size here. All right. Now the sum of all these values, sum of all these quantities in the last column is known as sum of square between. This is nothing but between. We are just squaring here, right? And then adding them all up. So that's why it's called sum of square of the variance between the groups. This is that quantity here. So once you have this, the next quantity that we have to calculate is something called mean square between, okay? Mean square of between variance. It is just a ratio of sum of square between this number divided by the degrees of freedom. And degrees of freedom here is number of groups minus 1, which is 3. So the quantity here is this one, okay? So this is an important quantity. So all these calculations we are doing just to calculate our F test statistic, which was a ratio of variances, right? So we are done with numerator here. Now we need to get the denominator part. So for the denominator part, we need to get the within group variation. So within group variation again, so here I am just showing for one group here. I know in the previous slide, the values for each group were in a horizontal row. Here I put them vertically so that I can show the calculations of what we are doing. So for the first group, we had 4 readings here. So you just take the difference and square them up. So the within group variation is also known as error variation. Okay, error is more commonly used, but it could be within also in some places. So for the first group, I got this number, and for the other 3 groups, if you follow the same procedure, we should obtain these numbers. So what was the step after getting sum of squares? We need to calculate the total sum of squares, which is the sum of all those individual groups, and you get the degrees of freedom. In this case, the degrees of freedom is the total data points minus the number of groups, which was 16 minus 4. And you calculate the mean square error. Mean square error again is just the ratio of sum of squares by degrees of freedom. So this is this. So for our F statistic, we got numerator in the previous slide. Now we have the denominator. Okay. Now let's just summarize whatever we have done here. Okay, now these are the formulas. If you had to get these formulas initially, it might have been a little overwhelming, but now I think you can very easily relate to all of this, right? So this last column is called mean square error, which is, mean square of groups or treatments. And this is mean square error or within. So the formula was sum of square by degrees of freedom. And how did we get sum of squares? We calculated the variance like this, okay? So all this is saying is yi bar is nothing but, this is the average, it's the group mean. It's just the notation for group mean here, okay? And y double dot bar is the overall mean or the grand mean. That's all. All right, so using this following this formula procedure, we obtain sum of square treatments. And so, okay, this is nothing but there is something called ANOVA partitioning. So we calculated sum of squares of treatments or between, and sum of squares of errors, right? So what ANOVA is doing is it's just trying to separate the variation in the data into these 2 components, like sum of square between and sum of square error. These 2 together is known as sum of square total. This is called ANOVA partitioning, okay? That is what they have split here and shown. Now, let's calculate the F statistic. F statistic is, as I said, just the ratio of these 2, okay? So the value that we obtain here is 12.73. Now let's remember this value here. Now let's do the inference. Again, the same procedure that we followed for t-test. We have the F test statistic from our data. We have to obtain F critical value from the distribution table. As I said, F distribution has separate table for each significance level. So for our significance level of 0.05, this was the table here. As you can see here, the two things that we need once we identify the correct table are degrees of freedom, 2 degrees of freedom. It's nothing but this is numerator degrees of freedom, and this is denominator degrees of freedom from our F ratio. So the numerator degrees of freedom were 4 minus 1, right? Because we had 4 groups. And the denominator degrees of freedom were number of data points minus number of groups. So we had 16 data points, 4 groups. So that's why it's saying F312 and significance level of 0.05. So we'll just have to find that here. So for the numerator degrees of freedom of 3 and denominator degrees of freedom 12, this is our value, 3.4903. Okay. So I think you can already make an inference here, right? So our calculated test statistic is 12.73, which is very extreme when compared to the table value from the table. So we say that this value is so extreme that the means, the difference in the means is not by chance. There is some variation because of the type of formulation that you use. So we reject the null hypothesis here. Okay. So we just quickly go to ANOVA and Excel and Design Expert and see how to do this. Okay, you should again be seeing the Excel sheet that we use for t-test. If not, just let me know. So I have set up the data here for conducting the ANOVA, right? So instead of, we had the values for each treatment. MT1 is just mixing technique 1 and all that. So each treatment, instead of the rows, I put it along the columns here. It doesn't matter which way you put, but I just put it vertically. So again, you'll go to data tab here. We'll go to data analysis, and now you have to select ANOVA. We are doing ANOVA single factor. Now, again, there are different types of ANOVA here, like 2-factor ANOVA, 3-factor ANOVA and all. But for our example, we are concerned only about 1 factor, right? Just the type of formulation. But in some cases, you might have 1 more factor, like the type of raw materials that you're using or whatever. So that would be multi-level ANOVA, which I'm sure you'll cover in the next sessions. But so we'll select single factor here. We'll say okay, and then we have to give the input range. It's nothing but you'll just go ahead and select all the data points, all the groups for the ANOVA. And it's again asking, do you have labels or the column names, identifiers in the first row? You'll say yes. By default, the significance level is 0.05. We don't need to change that. And output, I want it into the same sheet. So you'll just select cell from here and say, okay, it should give the ANOVA. Okay. So we did so many calculations. We will never do in real life research applications or analysis. We'll never do ANOVA by hand, but I think it's very useful to do some examples by hand so that we understand, otherwise it will be confusing. So I believe we got same answers here. Our test statistic F, okay. So the first table is nothing, it's just calculating the descriptive statistics, basic statistics for all the groups. The second table is ANOVA here. See, this first row is for between group variation. I think we got the same values. If you look at the t-test statistic, which is the ratio of these two, it's 12.72. We got something closer, right? And the F critical value from the table is 3.49. So again, depending on this, we say that null hypothesis can be rejected. Or looking at the p-value, if it is less than our alpha, we say that the results are significant. That means there is a significant effect in the different formulation techniques that we are using. So you can choose any one parameter or any one quantity to make your inference. Most people might prefer p-value, but choosing F statistic is not wrong as well. And I think we will go to Design Expert and show this again. So I already have Design Expert open here. I'll select a new design. So I'll go to File, New Design here. Okay, So in order to conduct the ANOVA, the option that you have to choose in Design Expert is called multi-level category. We only have one level, we also have multi-level here. We'll see how. So we'll select multi-level category. We have only one categoric factor, that is the type of formulation. So you will just go ahead and give some name here. This is just an identifier for you. So I'll just say motor formulation. Okay, and the units are nothing but what is the thing that we are studying here, right? So we are trying to study the mixing techniques, if it has any effect or not. So we'll just say mixing technique here, and it's asking how many levels or how many groups. We had 4, so we'll say 4, and it will make 4 rows here. So you can just give some name to identify each of the levels. So I'll just say mixing technique 1, 2, and so on. All right, and it's asking how many replicates. Replicates are nothing but how many samples you have or how many observations you have in each group. So in each group you had 4 replications, right? So overall we had 16 runs. So this is your setup, and you'll say next here.
Excuse me, madam, the screen is not shared, madam.
Oh, I'm sorry. Let me try. I'm so sorry. Okay, are you able to see now? There should be a design of expert screen. Sorry, design expert screen.
No, not yet, ma'am.
Okay. Now, sir?
Yes, ma'am. It's okay now.
All right, okay. Thank you. Sorry, thank you for your patience. Okay, so all I did here was just to go through quickly. I went to file, I chose new design option here. Once you do that, you will see these options on your left side. You can select multi-level category, and then it will just ask how many categoric factors you have. We have only one type of formulation. I just gave some name here, and I mentioned how many levels do we have. So we have 4 types of mixing techniques. So I gave 4, and you can select a name here. I just said 1, 2, 3, and so on. So this should be 4. And then it's asking how many replicates, nothing but how many observations you have in each group. Okay, so I said 4. So overall we have 16 runs. That is the basic setup. Now we'll go to next here. So in the next, it's asking how many responses are you studying. So we are just studying one response, which is the tensile bond strength. So I'll just say 1 here. It's asking, give some name to your response. So we'll say tensile bond strength. The units were pounds per square inches. So we'll just put that here. And we can ignore all this for now. We'll say next. Let's see, finish. Okay, so what it does is it sets up an experiment for us, right? So, but we already have the data. So this is like a blank sheet when you're starting a new experiment. It's saying in what order to take the readings. It's suggesting to take mixing technique, second reading, 1 first, and then go to third reading. So it's just randomizing the order in which you are taking the readings. So this will be helpful when you are conducting a new experiment. But since we already have the data here, we just copy paste here, right? So I already have the data in my Excel sheet. So the way I have data is I have all the first mixing technique values together, and then I have second mixing technique values and so on. So for me to copy paste in this order, we should go to design expert, and I have to make sure that all these mixing techniques are in that order. All the first mixing techniques are first, second, and so on. So how you do is if you just double click on this factor 1 column, it will just automatically sort those. Okay, so now you can see they are sorted. So now I can go back to Excel, just copy these values. Go to design expert. So in order to paste this, you have to click on the column heading here on the response section, and I'm just pasting here, or you can use this option also to paste. So now you have all your values. That's all we have to do. In the background, I think the analysis is already done. So once you have your data, you can see the analysis tab here. If you click on tensile bond strength, we don't have to look at this right now. Since we are studying about ANOVA, we'll go to ANOVA option here. I am not sure why that is coming up. I should confess that this is the first time I have looked into Design Expert. I use other softwares like Minitab, SPSS, and all that. I have not used Design Expert. So Pardon me if I'm doing anything wrong. I hope you'll learn more in the next sessions. All right, so there's a lot of information that ANOVA has given, this analysis has given here, right? So we will look at the ANOVA, this section here. So what you can do is you can change your view. If you see this is the window, this is showing 4 options. If I just want to see this window, you can just go here and choose that option. You'll have only that thing, everything will be removed. So all we have to look at is if we got the same results or not. Again, even from the design expert also, we got the same F value. So our analysis was right, okay? So I'll go back to my PPT and see what I have next. Okay. Cool. So there is an important concept called ANOVA assumptions, right? So before we conduct any analysis, we assume certain things about the data set that we have. The number one basic assumptions that we make is normal population distribution. That is, we assume that the sample data that we are collecting for a process, that process itself follows a normal distribution. If we have multiple levels, we assume that each level follows normal distribution, okay? The second important assumption is called constant variance. So we assume that there is not like lot of variance in the data. That is an assumption. The other assumption is called data independence. So we assume that one level does not affect the other level. That is, mixing technique 2 does not affect the readings that we obtain from mixing technique 1 for whatever reasons. So these are like the basic assumptions here. So what we do is, in order to, the assumptions, we rarely check them before conducting the analysis, because it's not easy to find a data set that can satisfy all the assumptions, right? So we'll get a data set as best as we can. We'll go ahead with the analysis. If we get significant results, then we'll check the assumptions to make sure that we have fit the right model. So the assumptions are actually not checked with the actual data points, but they are checked using something called residuals. Okay, a residual is nothing but, say Yij is your observation, is your actual observation. Okay, but Yij, this one is like the predicted observation. Like your sample, the mean strength of the motor formulation 2 might be something else, but from just your sample, you got one value. Okay, so residual in simple words is nothing but it is the difference between the actual value and the value that you assume that it takes. So that is called as residual here. We want to have this error as minimum as possible. Okay, so we check all these assumptions for residual values. Again, it's important because we want to make sure whether we have fit the right model or not. And in order to check these assumptions, we make use of certain plots. For normality assumption, we'll make use of normal probability plot. Independence assumption, we'll plot the residuals versus the run order. Okay, run order is nothing but the order in which you collected the data and all. For constant variance, you'll check the residuals versus the predicted values, the values that you hypothesized. And just so these plots would be automatically generated in Design Expert. All right, so you should see the Design Expert screen. In case it doesn't show up, just let me know. All right, so again, Design Expert window here. So you can select the Diagnostics tab here. Okay, so diagnostic tabs, it calculates many different types of plots, but for our analysis, we'll just stick to what we need. So the first one is normal plot of residuals, right? So again, let's look at only this plot. So one way to check whether the data follows normal distribution or not is that if you take a pen and try to line it on this plot, almost all of the data points should be covered by that pen. You know, some can fall outside the range, but at least most of them should fall on the line. I think that assumption will be satisfied here because most of the data points are falling on that straight line. Okay, so we can say that normality assumption was satisfied. And if we go to the next chart here, which is residuals versus predicted. So residuals versus predicted, it checks the constant variance assumption. That is, let me just bring it up to the front. Okay, so the data points are kind of randomly scattered. So the assumption is violated when we can see a funnel shape like this, like an outgoing shape. You know, like the values are closer here and then gradually they are going apart, or the values are very far away from here and they're gradually coming close like that. If we see values like that, then we say that no, there is some other factor that is affecting the values. Okay, the residuals are not random. There is some other factor that is pulling the values, which we did not consider. So in this case, we can assume that the assumption is satisfied because the values are not that far away. You can argue that maybe this value is far away, but we can still ignore it as long as there is just one or two values, but then you can investigate it further. If you click on this, it shows which value is that, okay? It shows it was run 9. You can go back to your table and see which model formulation was run 9, and then you can see why that could have been different, or you can do further analysis, okay? And the other plot was residuals versus run order, okay? So this just shows the independence of the data. That is, there is no relation between, there is no effect of one model formulation technique on the other. Again, this should be like random. It should not have a particular pattern, like slowly outgoing or, you know, slowly coming close together. So we can assume that all our assumptions are satisfied here, or almost satisfied. And we'll see what I have next. Okay. All right, so these are the steps here. You'll conduct the analysis, you'll do your inference, you will check for your assumptions, okay? And then the other important concept is called outliers here, right? So outlier is nothing but it's just any extreme value. Say, for example, you had a normal distribution, normal probability plot that we checked in Design Expert. Almost all the values are around this line, but there is one value which is like far away from the plot, right? Now this is called an outlier, which is an unusual value, which is not an expected value. Now there are two things here. We cannot ignore outliers, right? Because sometimes they can be valid outliers, which are important for the data. We have to include them in the data. Sometimes they can be invalid outliers, okay? So how do you identify? There is a, you have to clearly identify what to do with the outlier. For that, you need to have domain knowledge, okay? I'll just give an example from my research here. So in one of the crime projects that I was doing, I was analyzing the crime data in the US from 1990 to 2015. In one instant, in Oklahoma State, right? In Oklahoma State for 1995, I got murders around like 258, okay? My analysis captured this as an outlier. It came out as an outlier, this reading. I was not sure why. So from 90 to 94, all the murder rates were like less than 50 or something, okay? And even from 96 to rest of the time, it was between 50 and 100. It was never 258, okay? But my analysis caught it as an outlier. Now, what do I do with it? I just did not understand why that is an outlier, because to be honest, when I started, I don't have much knowledge about criminal justice domain. Okay, this was the first time I was working on, so I don't know what decision to make. So I went to my professor, I showed him this. So he's an expert in criminal justice research field. He immediately identified, saying that, oh, that was because there was a bombing in Oklahoma in 1995, which killed almost like 160 or around 200 people or something. So that drove that murder number up. So is that a valid outlier? Yes, it is a valid outlier. But I didn't know that, but because he has domain knowledge, he could immediately identify. So like that, whenever you are conducting experiment in any field, you should have knowledge about that field. You should be able to identify what is a valid value and what is not a valid value. And once you identify that it is a valid outlier, then you have to determine whether you want to include that in your analysis or not. So in this case, we just wanted to analyze the general trend of the crime. So these are one-off events, right? They don't happen very frequently. It's just an outlier. So we didn't want that to influence our analysis. So we made an informed decision to remove that outlier from our analysis, all right? The other times could be an invalid outlier. So the other example was in Texas, in a small city in Texas in 1993, I got robbery rates like 1010 and auto theft like 1018 or something like that. They were like very big numbers for a very small town, for less than 5,000 people, right? How can you have 10,000 robberies for less than 5,000 people? So this is clearly a case of data entry error. This is an invalid outlier, okay? So that way you have to identify, and then you have to make a decision whether you want to include it or not. Again, statistically, this formula, it will give us identify whether a data point is outlier or not. It will do that internally. It will make use of the residual and the mean square error, and then depending on that value. So it says that if we get this value like more than 3 or 4, then that is a potential outlier. That is how it flags the outliers. And then what you do with outliers depends on your domain knowledge and your research objectives. So ANOVA, it just says whether the means are equal or not, right? So H0 was saying that all means were equal, all equal. And null hypothesis says not equal. At least one pair of means are not equal. That's all we'll know. We will not know, ANOVA won't tell us like which means are different. Okay, is it first and third mean or second and fourth? It doesn't say that. Once you get significant result from ANOVA, then you have to move on to post-ANOVA. You have to do post-ANOVA comparison of means. There are many ways to conduct these analysis. The graphical comparison of means is just that some people, they plot graphs and they try to visually identify, but that is like a brute force approach. It's not robust, right? So we have other statistical tests like Tukey's test, Fisher's LSD and all. So you can choose any one of these depending on your experimental setup. And it's not necessary to do more than one. We can choose any one and do that. And I think in this example, the Fisher's LSD was used in the design expert. So all Fisher's LSD does is, it says that if the difference between any two means is greater than this calculated value here, then those means are significantly different. Again, this LSD or the least square difference is just calculated using this formula here. I think design expert shows this. I just want to quickly show where we can see that in design expert, because that is important. Once we conduct the ANOVA and if we get significant results, we have to report which means are different. All right, so I'm again going to the design expert window here. So let us go back to ANOVA tab. We'll open up, okay, treatment contrast. Okay, so you can see your treatment contrasts option, and it compared every mean here, and then it said whether that is significant or not. So again, 1 versus 2, its p-value was 0.039. Is it less than 0.05 or significance level? Yes. So we say that that is a significant difference. 1 and 2 are different. Now you might have a question here that the reason we took ANOVA was we didn't want to compare two means at a time, right? Like we didn't want to do these many means comparison. But these these post-ANOVA methods, what they do is instead of taking 0.05 significance level for each test, they distribute that 0.05 among all the 6 tests. So for one test, it will not be 0.05, it will be by 6, like, I'm not sure if it is exactly by 6 how it calculates, but it distributes that significance level among all the treatments so that your overall error rate, your overall family or experiment wise error rate will still be 0.05. Okay, so this table shows us which means are significant. So in our result, once we say that ANOVA results are significant, then we list out which means are significant depending on these p-values here. Okay, almost all means are different except 1 and 3. They are almost close because the p-value is very greater than 0.05. Okay, and I think the next concept is regression. I know I spent a lot of time on ANOVA analysis because that is like the backbone of DOE, and regression is almost it is done for every DOE experiment, but once we understand ANOVA, all the concepts should be simpler here. But if I had more time, probably I could have gotten much deeper into this. Okay, so regression is nothing but it models the relationship between certain set of variables, right? Say for example, you want to understand how salary and experience, level of experience are related. Okay, so you want to see if experience, number of years of experience has a positive effect on salary or not. So here your variable of interest, okay, the variable that you are interested in studying is salary, which is known as your dependent variable or outcome or response variable. And the other variable, experience, whose effect you want to study, are known as independent variables or predictors. Okay. Now, if you have only one independent variable, that is known as simple linear regression. If you have more than one independent variable, say along with experience, you want to see whether, let's say what degree level, what kind of degree they have, whether that has any effect on salary, and also number of publications. Do these also have any effect? When you take more than one independent variable, then that will be multiple linear regression here. Okay, so all regression does is it tries to fit a straight line to your data. It tries to fit a linear model to your data. Okay, so here this is an equation of a straight line, right? So x is your independent variable, And beta naught and beta 1 are called coefficients or estimates. So beta naught is not useful in all the cases. So we mostly focus on beta 1, just the coefficients that we get for our independent variables. If you have more than one independent variable, this equation would be, say, beta 1 times x1 and beta 2 times x2, right? So just depending on how many independent variables you are taking, you will have those many in your equation. So beta naught just says, it tells us how much effect does each independent variable have on the outcome. We'll see that with an example soon, but let's try to understand the actual methodology behind the regression. Like, how does it build that model? How does it fit the regression line? So in this example, I have just gotten this data set in which this was the, I think, data of around 105 students. We wanted to study the relationship between their high school GPA and university GPA. We wanted to see how does that affect. If somebody gets a good high school GPA, do they also get a good university GPA? Intuitively, we will say yes, but we just wanted to model it and see. So these were all the data points. Once you plot this, you can see that, yes, there is an increasing trend. If you get good school in your GPA in your high school, you'll get good GPA in university also. So this line in orange is the important line here, right? Because our regression model or the regression equation would be the equation of this line. So this is called the best fit line. All right. So how is this line obtained? Now for that data set, say these are all the data points. Now that line could have been like this or like this. It could have gone in any direction, but why did it go only in that direction? And how does it decide how to draw that line? Okay. So the basic concept here is, it's the ordinary, there are many different types of regressions like ordinary least square, weighted least square, but ordinary least square using the least squares method is the most popular algorithm here. So say, for example, you have multiple data points here, right? So the regression technique, what it does is it fits a line such that the vertical distances of these points from the fitted line. So remember, these are actual points. These points which are outside the line are the actual observations. We are trying to fit a line to that, okay? So the line is fit in such a way that the vertical distances from each of these points, okay? Let's say, so this is again residual here. Because residual is, remember, it is the difference between actual value and fitted value here. So this is our actual value, but the line said that for this corresponding X value, this should be the Y value according to the model. So this is our predicted. It's actually called, I think, Y hat, and this is your actual value. So your residual is nothing but it's the difference between these two. Okay. So what least squares technique does is it tries to minimize the sum of square of all these residuals. That's all it does. It tries to calculate this difference, vertical distances of each possible line, and it tries to square them and sums, and it says which line gives the minimum of this value, and then that would be the best fit line. All right. Now, I just have an example for this in Excel. We'll just again go back. Okay, so you should be able to see an Excel now. If not, just please let me know. So I just have a sample data here. So in this, we have data for 10 students. And I want to see the effects of IQ, student IQ, and study hours, number of hours they study. Maybe this is a week, probably. We want to see how these two factors affect the test score, what kind of relationship they have, right? So let's see. We'll again go to the data analysis tab here. And now this time we will select regression. Okay. And you have to give the input Y range, that is your dependent variable. And your input X range would be all your independent variable columns. So these two, you just select all of them at once. And it's asking whether you have labels here. Yes, we don't have to worry about confidence level now. Anyway, it's by default 95%. And the output range, again, I want to have it in the same sheet. So just select any cell over there and now say, okay. You should get the output here, right? Okay, so let's try to interpret this. All right. Okay, so see here, this is, it doesn't ANOVA internally, but for our regression, we are mostly focused on the regression coefficients here, right? So as you can see, it has calculated regression coefficients for intercept and our two independent variables, IQ and study hours, okay? So it's saying, okay, I think it will be better to write down the equation and then we can interpret. I'm just noting down those values in a paper here. So our beta naught is 23.15. The coefficient for IQ should be 0.51. Coefficient for study hours is 0.467, right? So, okay, we'll write a regression equation for that, but we can look at some other things here, right? So it's saying p-value. Let's forget about intercept. It's just to, to fix our line in the plane here. It's not useful in all the situations. So let's look at the p-value for IQ and study hours. So it says the p-value for IQ is 0.025. Is it less than our significance level? Remember, the confidence level was 95%, right? So the significance level would be 0.05, and this is less than that. So we say that yes, IQ has a significant effect on the test score. Similarly, even study hours also have less than 0.05 value. We say even that is significant. Now let's go back and try to write our regression equation. Okay, so two main uses of regression, right? Again, as we see, first one is to identify which factors are significant. We have already seen that, which independent variables are significant, okay? And the second use of regression is to be able to predict new values, okay? That is really important, and actually linear regression is one of the basic, most important algorithms in machine learning. There are many more complicated, but linear regression is like the basic algorithm. That's the basis for so many machine learning concepts. So second use is to make predictions about a new value. All right. So how do we make predictions? Is looking at the regression equation. Okay. So if I write down the regression equation here, so say y was our independent variable, which was test score, and it should be beta naught plus beta 1 x1 plus beta 2 x2, right? And beta naught would be our intercept, which was 23.15. And beta naught is 0.51 into, this was, I think it was IQ, and beta 2 stars study hour, okay? Beta times study hours. I'm sorry, I should have written the beta 2 value here. Beta 2 was 0.467. Okay, now how do we interpret this regression coefficients? That is very important. As I said, intercept may not be useful at all times. We'll just ignore this for now. Now let's look at this. It says 0.51 times IQ. So what this means is for 1 unit increase in IQ, okay? So 1 unit increase in IQ, maybe 1 point increase in IQ will result in 0.5 points increase in your test score. Okay? That is what this effect is, like how much effect. We already know because of the plus sign, it has a positive effect. But by how much effect, how much positive is this coefficient estimate? Okay, it says if you increase your IQ by 1 unit, that means you will score 0.5 units more on your test score. And this is assuming that all the others are constant here. These are just individual interpretation. Okay. Now again, if you look at study hours, this is 0.467. I pardon for my terrible handwriting today. So 0.467. What this says is for one, if you study for half an hour more, let's just say that that value is 0.5. If you study for half an hour more, no, sorry, it won't be half an hour more. It is always 1 unit increase in your independent variable. So if you study 1 more hour, if you increase your study by 1 more hour, your test scores will increase by 0.5 units. So that is the interpretation of the coefficients. Now, how do we make predictions here? So predictions is nothing but if you want to predict the score of a new student, right? Say you have a new student and you know his IQ score is, his IQ is 98, for example, and you know that he studies on an average of 25 hours every week. Now, because you have this regression equation, now you can make predictions. You can say that, okay, if somebody has an IQ of 98 and he studies for 28 hours, 25 hours or something, then he can get this much score on the test. So that is how you make predictions about new values or, using the regression equation. So I think that's all I had for today. And yeah, I'll try to answer any questions that you might have, and thank you for your patience throughout.
Thank you, madam. I think you have taken complete 2 hours positively, and 10 minutes are also left. I was worried whether you will be able to complete in time, but I think you have managed it to give both examples and Excel and even design of experts. So, any queries, please, part from the participant side. You can unmute and may speak directly, please. Hello. Or you may also type in the chat window. Yes, sir, please. And if you have any queries, you may also mail at the email ID that which is provided.
Yes, please.
And, definitely.
Any questions that you might have, anything, any further discussions or collaborations, please feel free to reach out to me at that email.
Excuse me, ma'am. I have one doubt.
Yes, sir.
Yes,
You're talking about type 1 error and type 2 error.
yes, sir.
So in that, for type 2 error, the things will worsen. If means I'm little bit confused now. We have to increase the confidence level or decrease the confidence level for the type 2 error.
Yes, sir. Okay, so as I was trying to explain it, we have to make a judgment call, right? We have to determine how much error we are willing to make, how much mistake we are willing to make, and with which error we are comfortable making. Okay, so it will depend on the process that you are.
In that case, we have to go more than 95% or less than 95%.
It depends, sir. So in Six Sigma processes, right? So they go with 99% significant level because they don't want to have any defects in their process. Say, for example, automobile engines and all, or aircraft engines. It's right. You want to be very confident about your process.
So it depends on the judgment totally, I think.
Right. Yeah. It depends on judgment and also the after effects. Right. So what is the cost for you? What is the cost for business and what is the loss for the business if you make a wrong judgment? So, how much is it okay to make? It's not that bad, or no, you have to be very strict. Like, for example, if you make a faulty part in a bicycle, it may not result in a loss of life, right? But if an aircraft engine fails, then it is catastrophic. So depending on that, you will decide how much percentage you want to be confident or not.
Okay, thank you, ma'am.
Sure, sir.
Any other? The participants, you can please unmute and you can speak. I think that was. I think that is what is important when we way to compromise and way to make that judgment, and that is the whole purpose of doing this study from the beginning. And preliminary and pilot experiments will help us a lot in identifying these kind of things. First, if we can have thorough understanding on these variables or parameters and the levels, and once that is done, then we can jump to the main experiment. And these tools will help in deciding those things. So statistical is one aspect, and the other aspect is the inference that we make, and all this comes from the vigorous experience that we have on the domain that we choose or that on which we are trying to work on. Yes, ma'am. So if anyone has any other doubts, you may ask, or otherwise we may end the session. I have already shared the feedback link in the chat window. You may use that. And I would like to thank Madam for giving us the complete understanding on analysis of variance and the regression analysis. And I like the comparison between the different tests that we have performed, when to carry out these tests, hypothesis, and in a very simple and easy to understand examples. And especially when we have this Excel tool, and then we have so many other softwares available now. Yesterday also we had many participants asking for different versions of softwares and different packages already they are using. So Excel is very easily available, and many of them already are using. So I think that will serve, these examples will give us a little boost so that we can introduce many more tools. And today afternoon session also, we are trying to introduce factorial design. So I think with this continuation, it will now, everything will patch up. And I think now they will be able to do that minimum hypothesis test and hands-on hand calculations on their own. Using Excel sheet, they may include many more multi-variants and all, and that will give us a better understanding. So I hope everyone has made a best utilization of this session. And once again, thank you, madam, for taking time out, and in spite of your busy schedule, giving us time. And I am again requesting for giving us time for the next session as well. So
take it on my time, morning time.
Sure. I'll
try to
definitely this time. Definitely, I'll try to schedule at least one session of yours at the evening sessions. Probably after 4 or 5 could be better, I suppose. So I'll try to adjust it that way.
7 a.m. morning, it is fine. But I'm just an early sleeper. But I am very glad I was able to attend this. I hope I did a good job. I was really nervous presenting to such highly accomplished people over there. But anybody has any questions, just please feel free to reach out. I'm sure these topics like very confusing, and I tried my best. But thanks for the opportunity, and for your kind acceptance and everything. Your HOD sir, principal, so they were like really nice, and I'm glad I got to talk to them. So thank you, Varun. Thank you.
Thank you, ma'am. Thank you, everyone. So you can fill the feedback forms, and we'll join again at 1:30 with the same link, and we will continue with factorial design.
Thank you all. Have a good day.
Thank you. It's 2:30, I suppose, right? 2:30. Okay.
2:30, like 1:30.
Okay, 1:30. Fine.
Sorry.
Okay. Bye.